Hey guys, in this video we're going to be covering target 2C.4. Our mastery learning objective is I can factor quadratics by recognizing the difference of squares. So difference we're going to subtract, and squares are going to be all those perfect squares that we talked about in that first unit. So a quick recap, if I have two binomials, a plus b times b minus a, when we do our Punnett square box, we want to make sure that we keep all the correct signs. So I have that a plus a b. I have that a and then minus b. Please don't lose those negative signs. All right, now I'm just going to multiply using my Punnett square box. So a times a is a squared, because when I multiply, I add exponents. A times b is ab. A times a negative b, keep it in alphabetical order, so a negative ab. And a negative b times a positive b is a negative b squared. So when I look at all of these terms, what ends up happening is I write them out, a squared plus my ab minus ab minus b squared. We notice then that that diagonal, right, those two terms in the center, end up being like terms that actually become a zero, right? So ab minus ab is a zero. So what I'm left with then is a squared minus b squared. And this is the format that I need all of these examples to be in. Because if it says difference means I'm going to be subtracting. Our squares, right? Squares is going to be the fact that each of these numbers has that exponent of a 2 or is a perfect square when I'm looking at the number value. So let's kind of practice some of these. So again, if it's not a subtraction, if we're not subtracting, we can't even really say that this is a perfect square. There are a difference of squares, and then the squares obviously have to deal with each number being a perfect square itself. So looking at this first example, example 1, I have x squared minus 16. Do I have a subtraction sign? Yes, so I do know that it is a difference. And now I'm going to check to see if each of these terms are a perfect square. So if I have x squared, bring that down, I want to take the square root of that. Well, the square root of x squared is just x. Do the same thing with the other term. Square root of 16. Now if you forgot perfect squares, you can go ahead and plug that in your calculator. Alright, so quickly checking the square root of 16, I'm going to go ahead and press Control and then x squared, and that's going to give me that radical sign. Type in 16, and I do get 4. So what that tells me then is that the square root of 16 is a perfect square because my answer is 4. Alright, now what I do after that is write my binomials, because I'm not done. I still need to factor this x squared minus 16, right? What that's going to give me is I'm going to have two binomials, and they're going to be in the format of the examples that we just had above, right? A plus b minus a minus b. So I'm going to have x plus 4, and then I also need that middle term to cancel out, so that I need the opposite, so x minus 4. All right, next example. I want to make sure that I remove any GCF. So always check a GCF if the x squared term is not a 1, right? I do see that 3. Can 3 divide 3x squared and a negative 12? And yes, it can. So in this case, we have to take our GCF out, which is a 3. So I'm going to divide each term by 3. And that's going to give me 3 times x squared minus, well, 12 divided by 3 is 4. And now I still see that that is the difference of squares. I see that subtraction sign, but I want to check to make sure that each of these terms do have a perfect square. So x squared, right, square root of x squared is x. Square root of 4, well, if I'm thinking of numbers that multiply to 4, that's the same number. Again, if you want to check it in your calculator, you can press Control x squared. The square root of 4 is 2. So that when I write my binomials, I do need that x plus 2, x minus 2, but I cannot forget that 3. Remember that GCF, that 3 right there? It has to be written in front of both of those binomials. All right, let's look at example 3. I do see that that coefficient in front of the x squared is bigger than a 1, but 4 cannot divide 9. So there is no GCF here. We're just going to have to see if each term is a perfect square. And it's also a subtraction, so I do know it's a difference. What I'm going to do then is I'm going to take the square root of 4x squared. Well, you have to do this in parts, right? I know we just did previously that the square root of 4 is 2, right? Looking at the previous example. And the square root of x squared is x. So the square root of 4x squared is just going to be 2x. Okay. Well, the next term, I have the square root of 9. Square root of 9, well, two numbers that multiply to 9, that's the same number, is 3. But again, yes, you can check it in your calculator. Control x squared, type in 9, and that would give you a 3. So our binomial here isn't just going to be x plus or minus the other term. It has to be 2x plus 3 and 2x minus 3. So again, you take each of those perfect squares, and you have to alternate signs. All right, next one. I see that n squared plus 9. There is not a subtraction sign here. Yes, I know that the square root of n squared is n, square root of 9 is 3, but this cannot be factored because it's a plus sign, not a negative sign. So I'm just going to say can't factor, because it's a plus sign, not subtraction. Okay, can't do anything with it. Go ahead and scroll down to number 5. Example number 5, I have 5x squared minus 3. Well, I do see that coefficient of a 5, but that isn't a GCF there. So I don't have any GCF because 5 does not divide 3, and neither of those numbers have anything in common. So when I take the square root of that first term, 5x squared, if I type that into my calculator, not sure if there's a square root of 5, so control x squared, type in 5, I get a decimal, 2.23607. That's not a nice number. So what that tells me then is that there is no square root of 5. This doesn't simplify. Alright, let's check the next one. Square root of 3. Is there a square root of 3? Is there a number that multiplies by itself that gives us a 3? Well, square root of 3 is also a decimal, 1.73205. So that also cannot be simplified. Alright, so what we have to say then is, well, this can't be simplified because neither of these are perfect squares. That's all we have to state then. Ignore that 2c plus or 0.5. So this can't be factored. And we can say not perfect squares. Board gets really weird. So can't be factored, not perfect squares. Alright, let's check this next one. I have example 6, 5x squared minus 45. I see that coefficient is greater than a 1. But can I divide 5 out of both numbers? And yes, I can. So our GCF here is 5. If I divide 5 out of 5x squared, that's going to give me x squared. If I divide 45 by 5, that's going to give me minus 9. And now I'm going to check to see if each of these has a perfect square. So I'm going to say x squared. If I take the square root of that, that's x. If I take the square root of 9, That's 3. There is a perfect square for each of these. So my final answer then would be 5 times x, my apologies, that should say 8 plus 3, not a 9. So it's going to be x plus 3, x minus 3. And that is our final answer. Okay, so again, if it does not have GCF and it doesn't come out to a nice square, you cannot simplify it. If you are adding, that is not the difference of perfect squares. So again, you cannot factor it. Only if it's a perfect square and we are subtracting. Go ahead and give 2C.4 a try, guys. Good luck.